Hello, everyone. In this project, the goal was to build a regression model to predict the average daily electricity consumption of the household using the RECS dataset. The evaluations measures is the MAE, stands for mean absolute error. So the main object through our workflow was to systematically reduce the MAE while ensure the model generalized well. In today's video, I will explain two things. How do we improve the performance of our regressor, and how do we assess and improve the model fit, including the learning curve and the validation. So for the beginning, we start with the importing the dataset, and the feature engineering is something later we did. So before that is we did base modeling pipelines, um, uh, try to do the missing value handling, one hot encoding for the categorical variables, and a boosting model that works well on the tabular data. On the early baseline model was the HistGradientBoostingRegressor, HGBR, because it's fast, robust, and usually strong on the structured data set. This gives us performance reference point on confirmed pipeline was correct end to end. So this help us answer two questions. Really is just are we run this model correctly with no leaking edge or formatting issues, and are we the performance range is right before spending time on advanced masters. So after that, what we do is trying to identify the weakness here is the categorical features and nonlinear relationships. So one hot encoding can create many spare features, but sometimes it's not the most effective, efficient ways to do it. And the nonlinear structure and screwiness target. So the electricity consumption typically has school distribution, might have nonlinear relationship with housing size and room and household characteristics. So the next thing we do is to improve the representation and handling these patterns. So we did feature engineering. We add more we add four common things into the model, and we did target transformation. This helps us to um, this is really helpful because the electricity usage often has a heavy tail. So the log transformation reduce the extreme influence and make the optimization smoother for the model. After prediction, we transform back using XPM1 function. And stronger model for character handling is a CatBoosting. So we did a CatBoosting into the model. Um, and also we do a stacking, which is Ensemble the large the two model together. The first one we did is the HGBR, and then we combine HGBR and the CatBoost using weight Ensemble. So testing the difference, we and find the best ensemble, usually leaning more towards CatBoosting, meaning the CatBoosting contribute more to the final prediction. And we we also use the clipping to control the outliers, apply the quantile base clipping for final prediction because MAE can harm by the extreme outliers. So we instead of guessing, we just do the clipping the prediction for a reasonable range using quotiles like 0.5% to 99.5% or just 1% to 99%. So this is gonna reduce the impact on extreme unrealistic outputs and improve the leaderboard's performance. And then what we did is we do the cross validation for K-field cross validation, uh, not just simply not just single slip. We use five-fold cross validation. This means we train the model multiple times on different slip, and if it give more stable estimate of the generalization MAE and reduce the risk, just one lucky slip that makes the model look better than it really is. Um, so also we did a auto-fold prediction for stacking and ensemble tuning. Um, this is gonna ensure the way more reliable. So the idea is each training row gets a prediction from the model that did not train on it. So auto-fold MAE is closer to real performance. Then we turn the ensemble weight and clip based on the auto-fold prediction. So this is more trustworthy method than tuning only on one handout split. And for the learning curve to assess fit, this is what we finally do is if both error are high, then that means the model are underfit. If training error is low, but the validation error is high, overfitting. If the gap shrinking with more data helps. If the data stay large, the model needs stronger regularizations or different features. So in this case, the learning curve help us to confirm our approach had manageable generalizations gap. So when the gap look too large, we'll adjust the tree dips, the L2 regularizations, subsampling, and the learning rate and the iterations. So the learning curve wasn't just for display, it actually guide us get our tuning decisions. So to summarize everything is we start with a stable baseline model, each HistGradientBoostingRegressor guidance boosting regressors, and then plus the pre-processing, and then we improve the performance through the feature engineering and log transforming the target. And we also put the CAD boosting to to the model and better handle the categorical features and achieve the further improvements through the and ensemble the tuning weight. And then we control extreme prediction using clipping, and we validate the model fit using k-fold cross validation and out of fold prediction evaluations to end the learning curve. So this allow us, everything allow us here to systematically reduce MAE and improve the leaderboard result in a reliable prediction way.